We have misunderstood our own galaxy. For decades, we assumed planets were rare, but one NASA telescope, staring at the same patch of sky for 9 years, proved that assumption catastrophically wrong. Here's what we all believed before 2009. Exoplanets existed, sure, but they were hard to find, and the ones we had found were mostly monsters, huge gas giants sitting uncomfortably close to their stars, nothing like our own solar system. Fewer than 500 confirmed worlds existed in the entire human record, most of them found by watching stars wobble under a planet's gravity rather than watching them dim. That method only caught giants. Anything Earth-sized was effectively invisible. By the end of this video, you'll understand why that picture just collapsed, why the most common planet in the galaxy is a type we don't even have here at home, and why a machine NASA nearly declared dead in 2013 ended up rewriting the rules of planetary science anyway, and setting up every planet-hunting mission that came after it. The person behind this was William Barucki, a NASA space scientist at the Ames Research Center who spent years pushing the idea before anyone would fund it. He proposed watching stars for tiny repeating dips in brightness, the shadow of a planet crossing in front of its star. It sounded almost too simple, and NASA rejected the proposal 4 separate times over more than a decade, doubting the technology could ever be precise enough. Barucki kept refining it, building test observatories on a mountaintop in California to prove the concept could work before NASA would risk the money on space hardware. The agency finally approved it in 2001. It launched on March 7, 2009, carrying a 95-megapixel camera, the largest ever flown in space at that point, on a mission that cost roughly $600 million. Its name is Kepler, named after the German astronomer Johannes Kepler. Kepler's method sounds almost too simple to work. Point a telescope at one fixed patch of sky out toward the constellations Cygnus and Lyra. Stare. Watch for a star's light to dim by a fraction of a percent, then come back. Do that for over 150,000 stars simultaneously, for years without blinking. That dip is the signature of a world passing between us and its sun. Picture trying to notice a moth flying in front of a distant lighthouse from miles away and doing it for 150,000 lighthouses at once, every 30 minutes, for nearly a decade. That was Kepler's job, every single night. But that is not everything. The first results came fast, and they were strange. Less than a year into the mission, Kepler had already flagged over 1,000 planet candidates, more than double the total number of exoplanets humanity had confirmed in the previous 2 decades combined. Scientists expected a trickle. They got a flood, and the flood kept rising with every data release. That should have settled the debate about whether planets were common. It didn't, because as the candidates piled up, something odd emerged in the data. The single most common size of planet in the entire galaxy wasn't Earth-sized, and it wasn't Jupiter-sized either. It was something in between, a size class that doesn't exist anywhere in our own solar system. No planet orbiting our sun fits that description. Not one. And wait, there is more. Astronomers started calling them super-Earths and mini-Neptunes. Worlds bigger than Earth, but smaller than Neptune. Some rocky, some gassy, some something in between that we still don't have a clean label for. Imagine walking into a room expecting to see either mice or elephants, and instead finding that the room is packed with an animal you've never seen before. That's what Kepler found. Not rare, not exotic, the default. But that's not the strangest part. As Kepler kept staring, a handful of its candidates weren't just common. They were sitting in the habitable zone, the narrow band around a star where temperatures could allow liquid water to exist on a surface. And you won't believe what else they found. One of them, Kepler 452b, got nicknamed Earth's cousin, roughly 60% larger than our planet, orbiting a sun-like star at almost exactly Earth's distance, with a year just a few days longer than ours. Another system, Kepler 186, produced a planet called Kepler 186f, close to Earth's size, sitting inside the habitable zone of a smaller, cooler star. For the first time, humanity had a real, documented candidate for a rocky world where liquid water might survive. That should have been the triumphant ending. It wasn't. In May 2013, disaster hit. Two of the four reaction wheels that kept Kepler precisely pointed at its target field failed. Without stable pointing, the entire mission, the whole planet hunting method, should have been over. Engineers at NASA refused to let it die. They came up with a workaround nobody had planned for, using the gentle, constant pressure of sunlight itself, pushing against the spacecraft's solar panels to help balance it like a spinning top balanced on a fingertip. They called the rebuilt mission K2. It shouldn't have worked. It did. Kepler, running on a jury-rigged fix using sunlight as a substitute gyroscope, kept hunting for planets for 5 more years. A telescope built to run for 3.5 years, crippled by a mechanical failure that should have ended it, instead operated until 2018, nearly triple its planned lifetime, before finally running out of fuel, more than 90 million miles from Earth, too far away for any repair mission to ever reach it. By the time it went silent, Kepler had confirmed more than 2,500 exoplanets, with thousands more candidates still waiting on follow-up. And here's the part that quietly rewired one of the biggest questions in physics. If planets, and potentially habitable ones, are this common, then where is everybody? That question has a name, the Fermi paradox. Before Kepler, you could argue Earth-like worlds might simply be too rare for intelligent life to arise elsewhere. Kepler removed that excuse. The real estate for life turns out to be abundant. The silence isn't. But Kepler was never designed to answer the final question. It could tell us a planet exists, and roughly how big it is, and how far it sits from its star. It could not tell us what that planet's atmosphere is made of, or whether anything is breathing it. That answer needed a different kind of telescope, and Kepler's data quietly built the target list for it. Within a year of Kepler's shutdown, its successor was already in orbit. TESS, the Transiting Exoplanet Survey satellite, picked up the same transit technique and pointed it at brighter, closer stars, scanning almost the entire sky instead of one fixed patch, hunting for the best nearby candidates for closer study. And waiting behind TESS was something even more powerful, the James Webb Space Telescope, capable of splitting starlight passing through a distant planet's atmosphere and reading the chemical fingerprints left behind. Water vapor, carbon dioxide, even gases that, on Earth, only exist because life keeps producing them. The mission that once could only detect a shadow can now, through its successors, start reading what that shadow is made of.